first speaker, I've been told, drives around in a DeLorean. So I'm hoping I can take on the Marty McFly role and he can teach me about flux capacitors and I can ride off on a hover skateboard. That'd be fun. So the first speaker, he's a strategic aerospace manufacturer and has led technology for large-scale organizations and diverse missions. He's the aviation entrepreneurial CEO and chief digital officer for Airship Technologies. Something to do with this cool craft right here. And the Airship Endurance VTOL, UAS, and Airscape Intelligence as a Service. I can't wait to hear what all of that is. And he's held various senior leadership technology positions, serving the Royal Saudi Air Force, Kingdom of Saudi Arabian International Airports, and Hughes Aircraft Company in Los Angeles. He's the board of director at the Evergreen Aviation and Space Museum. Please welcome Mr. Benjamin Barry.
So I'm Ben Barry, the CEO for Airship Technologies Group, and I actually have some members of Airship in the audience. Could you guys kind of show hands where you are? So they are amongst you today, folks. But we're really here to talk about this aircraft. This is our Airship B1. It's our smallest aircraft for intelligence, surveillance, reconnaissance. It's completely 3D printed. In fact, when we have this in production, we sell these with solar film for daylight flight. But think about solar cells on top of your buildings. They're about 6% to 8% efficient. This is solar film for the aviation industry at 28.8% efficiency. And the company we get that supply from just announced it's going to go to 31.6% efficiency. So where other competitors will fly for about 15 minutes, 30 minutes on one lithium ion or polymer battery, we can recharge that same battery during the daylight hours for 10 to 12 hours. And then we actually can add a hydrogen fuel cell for nighttime flight, which gives it even longer flight endurance. Now, there is a video attached to this PowerPoint, but we're going to pass that because it takes too long. It only gives me like 15 minutes to talk today. So this will give you some sense of what you're looking at here, but up on the screen. We actually 3D print these vertically, and I'll explain how we got to know how best to print these aircraft based on looking at some modeling. But you'll see the aerial view, lateral views, the internal architecture. Toward the end, we'll see the video of the aircraft flying. But here's a chart I really wanted to get to. We have competition today that are the 4, the 6, the 8 rotor drones. Typically, your hobbyist drones, you'll see them at the mall, cost anywhere from $300 to maybe $1,200. They fly 15 minutes, 30 minutes, maybe 45 minutes. And we did not want to become just another drone 1.0 technology amongst all the other drone 1.0s. So what we're talking about is clean technology, solar, and hydrogen fuel cell using electrolysis to produce the hydrogen for nighttime flight, long flight endurance. So it's solar during the day. This particular aircraft with a 50-watt fuel cell and one canister, about 29 hours and 57 minutes of hydrogen electricity, built based on the hydrogen. So now we're out to about 2.6 days of flight endurance. That's really pushing the competition in terms of how long can you keep the bird in the sky. That's the name of the game around intelligence, surveillance, and reconnaissance. This is the film that we use. In fact, I have a sample of that film up here. It's very flexible, very lightweight, and it can be applied based on a map based on the airframe surface. It also has dual junction capabilities where you can connect these on both sides of the film, and that's how they're getting to 31.6% efficiency around the solar film. 2 companies make it, one in Alta Devices out of the Bay Area, another in Microlinks in the Midwest. Alta Devices is at $100 a watt. Microlinks is at $300 a watt. So you guess which one we went with? Yeah. So what we ended up doing was mapping every aircraft, because we actually have 4 aircraft. And the way we get to 4 aircraft is we scale using the CAD to scale these up to different sizes, which gives us the ability to carry higher payloads. So the B-1 will carry a 3-pound payload, principally for cameras or intelligence, surveillance, reconnaissance. But the mapping is such, you can't just spread the solar film all over the aircraft. It actually has to use standard sizes. So when you do that, essentially this is what you're getting. And we can actually add a hydrogen fuel cell tank under the belly of this aircraft to increase the endurance. So when it's all said and done, this is what it looks like. That's the B-1 aircraft. We have similar mapping for the B-2, which is 3.3 feet in wingspan. The B-5, which is a 6.6 foot wingspan. And the B-7 uses the same airframe, but we use higher RPM rotors to have even higher lift or payload. All right, so when we first made the initial prototype, this is the B-2, the little bit larger aircraft than this one. This is how we had to make it. We had to piecemeal it together and then really dial in the center of gravity, see what worked, what didn't work, and eventually we came out with an aircraft that could fly. Now, we said, well, there's got to be a better way to do this because we were looking at these new technologies, right? We could have gone and looked at tooling, mass production of the aircraft with tooling. The tooling for this aircraft would have been $132,000. And then you get one airframe that you can mass produce, right? But customers have sensors, and the sensors that they want can be embedded inside the aircraft, on top of the aircraft, underneath. So no way to mass custom based on customer demand. So we said, okay, there's got to be a better way. And we turned to the SR-71 Blackbird. Who knows this aircraft? All right. Well, actually, we turned to the new one. It's called the SR-72. So there was a modeler who was working on developing a 3D printed SR-72, and we got together with the modeler and we said, okay, well, how are you going to model this in 3D printing? Well, the first thing he told us he was going to be doing was using the print process with our CAD. So we use SolidWorks for our CAD, and so he was using, what was he using? I think he was using STL files for, actually he was using Lightwave site software. So aerial view, lateral view, the front view, and the 3D view. So we've got CAD, we could probably do the same thing, right? Then we said, okay, well, how are we going to mount this in your 3D printer? Well, his 3D printer was small. So he was going to mount it by segmenting, actually splitting the aircraft in half and adding little connectors to reassemble this. I said, I don't do that, but that's definitely a way to get around a small 3D printer. And then we said, okay, once you have those parts, well, how are you going to position it? Well, he's going to position these based on printing the aircraft vertically. And the reason you want to print vertically is because you don't want to have support material to hold up an aircraft that doesn't have a base being supported by the table printer. So if we can print the aircraft vertically, there's less support material that has to be applied to the actual object. I was, well, that's probably a good idea. And this is the way it was going to look in the aerial, the front view, and the lateral view, and the 3D. So we said, okay, well, that's good enough. So what does it look like once we're actually past this step? And he was using this tool called Simplified 3D. And the goal was to print the entire aircraft in one 3D printer ubiquitously across the entire, all three parts, plus the two connectors. So everything was going to be used, like you see here, and it was going to take X number of hours to print this aircraft. All right, so we said, okay, what do you do after that? Well, what he did after that was he actually got finished product. So he was using some kind of polycarbonate, plastic, if you will, and it turned out to look pretty good, much like his renderings looked like. And I said, well, that's pretty good. Could you print that rendering in a carbon fiber material? Because that's really what we wanted to print our aircraft in. So he sure did. He took the centerpiece, he printed the aircraft in carbon fiber. Carbon fiber is very lightweight, very strong, and that's the kind of thing that we want to use in our aircraft. But then he said he had to sand it. I said, what do you mean to sand it? Well, we got to put these parts together. We got to sand the seams. I said, well, that's going to be a lot of trouble with assembling stuff. And then after you sand it, it comes out looking like this. It's a pretty nice looking aircraft. But we said, we can't do all that in mass production. And so we said, let's take our 3D print, our CAD, and see how we can rotate. First of all, get a bigger printer. If we get a bigger printer, maybe, just maybe, we can print the entire airframe. And that's what we ended up doing. So we got it to a position where we could actually print the the V1 vertically. So it starts at the bottom, just like a regular printer, and it goes all the way to the middle and all the way to the top, and boom. All of a sudden, you got a complete airframe plus about 6 other 3D printed parts, like canopy, the belly hatch, the port for the camera, the 2 rudders on the back, and the tilt rotor on the back. All right, so that was going to be a workable solution for us. Then we said, okay, well, the thickness has to be dialed down. When we printed this aircraft, it was 1/10 of an inch. We determined that we can come all the way down to 0.03 inches, which is going to be a lot lighter, down to about 2 pounds for the entire airframe. Now we can add more payload. We don't have to have higher rotors to make it lift off. And this was our final rendering for not only just the V2, but now we could scale. We could take that same CAD, we could scale it smaller to the V1, we could scale it up to the V5, V7. So we proved that concept in that process. And then we began to look at the hydrogen fuel tanks and how we would position those around the aircraft. And that turned out well. And then we started working with Georgia Tech Research Institute because they have a antenna that will communicate with satellite. It's a 3D printed antenna that we now 3D print for the canopy. So the whole canopy is becoming functional. It's a satellite antenna which reduces the weight of that antenna for each of the aircraft and delivers multiple frequencies. And then we said, well, how do we move this around the world? So we said, let's turn to the cloud. Because we'll produce these for the US market, but we also want to go international. And so we said, if we can develop a process where we ink a strategic manufacturing deal with India, and I was in India 2 weeks ago talking to 4 companies in Beijing, China. I'll be there in mid-June talking with China Aerospace. A couple of the countries, Turkey, Scotland. If we can ink a deal where we can 3D print our aircraft based on knowing how to encrypt our CAD reporting and how to do metering of each aircraft, then maybe we have a solution for mass production. So we call this cloud distributed mass production. Now that's a big takeaway. Cloud distributed mass production. So we are actually using our digital IP to print an object from Oregon to a country like India and getting paid every time that object gets printed. That's kind of a unique business model. And then we work with that country on the components to do assembly and manufacturing. If we can do that, we can do that around the world and build the brand. So just as a example, we're using the cloud for the infrastructure. We're using 3 things: encrypted services from that cloud, we encrypt the CAD, and we have a metering accounting for accounts receivable. And then, of course, we work with multiple countries or customers around global strategic manufacturing, which is totally different than the current business models. The 3 of the 4 areas, we're in clean technology, software development, advanced manufacturing, and then, of course, our strategic manufacturing partners. What's important for those contracts is exclusive marketing rights in a country for the company of choice, strategic manufacturing rights, and then Airship airframe 3D parts. Every time we print an aircraft, we get paid. And of course, we work with them in supply chain production. How do they get to supply chain partners that will be consistent? Now, I do want to show you the aircraft flying. It's all based on this drone 2.0 technology, anywhere from clean tech propulsion all the way through scalable payload architecture. This is the real test. Will the video come up? Yes. You can turn the volume up a little bit. This was the second test flight of the V2 aircraft. This was our initial prototype aircraft. The goal here was to make sure we could control the airframe, the aircraft close in, 1 to 3 miles out with radio control. From there, we were taking it up to about 400 feet, which is the national airspace limit in the United States. But they can go higher, especially for military purposes. We also want to make sure that this aircraft could be for military, but also first responders, and also for precision agriculture. Some people say when they see it flying, it's kind of like a flying UFO. Who used to see Star Trek? I didn't make the connection until years later. I was a Trekkie myself. But the search and rescue part of this is important. Think about the camera mounted just underneath the nose. So the camera is actually sitting in the water, so the first responders don't have to get in the water. They'll be able to see on their smart devices what's actually happening with whatever they're looking for underneath the water. Most drone manufacturers hate water. We love water. You'll see the back turbine. That's the forward vectoring, so that once we're up to about 15 miles per hour, the weight of the wings takes over, and so we can use that for lift. And then we can dial down the laterals so that we can conserve power with the aircraft. It's part of our power management scenario. Now this is a pipeline. So we are looking at small drones now, but we will also go to medium size. It'll be 9-footers, these 15-footers, eventually be 30, be 60. So for Tech Watch for Airship, a couple of things I want to make sure you guys are aware of. We're doing an Airship Stinger for the U.S. military. We'll be doing that in first quarter 2017. It's called a Stinger. And then we also have a design for a Ray, Stingray. This is the Stinger. So it's about 7 inches by 7 inches. Again, using the same CAD. We're going to be reducing it down to a miniature, actual micro aerial vehicle. That will also have an interface with it'll have a solar film on it, but also an interface with Google Glass. So the soldier will be able to see what the drone is seeing as it's sent out for close air support, and then they'll be able to do voice commands for where it should go in terms of logistics. And then, of course, the submersible. This is a rendering of what that aircraft looks like. When I designed this aircraft, I made it to be also an underwater aircraft so that the actual ballast tanks are on the left and right of the canopy. There'll be gills or slits underneath that space on the aircraft. Inside will be bladders. So the bladders, when they're expanded, air and water can't come in. When they're relaxed, water comes in, the aircraft submerges. And that's it. Any questions? Just one question.
Are you working with third parties to develop sensor packages?
We on purpose decided not to make our own sensors. So we acquire the sensors based on our customers' use cases, whatever their needs are, and then we system integrate those sensors onto the aircraft. And that could be as simple as a camera, sensors a camera as integration, or it could be a hyperspectral camera for farmers. There's also sensors that will sniff and look at the light refraction for methane gas or the pollutants in the atmosphere. Well, thank you so much. It's been a pleasure presenting to you. Thank you.